In this section, we'll discuss about EMF or cell voltage, free energy calculation, electrical work calculation, and equilibrium constant from cell voltage. First question that may come to your mind, that why don't we get electricity in the following method? Hydrogen and oxygen giving H2O, and it's highly exothermic reaction. It gives off heat. That heat could be used in boiling water to steam, and a steam can run turbine which rotates. You might have seen that in Niagara Falls, in which have seen the waterfall can run the turbine and can generate electricity. So in this particular process, heat could be used in boiling water to steam. Then steam can force turbine to move around, and in other words, that can give electricity. Even though it's quite possible, but conversion rate is quite bad. Only 40% conversion from heat to electricity, or the method that I've shown on the top. On the other hand, if somebody uses fuel cell, conversion rate is much higher. So in other words, going through heat to electrical energy is not a very good idea, because heat has the randomness. Heat creates randomness. That means the molecules don't move in one direction, they move in all direction at random. That's why efficiency of it goes down. If all the molecules are moving in one direction and pushing the piston up, for example, think it this way. I have different molecules in the container. If these molecules all move in one direction, say this is a piston which could be pushed up, and that's how one can think about doing work. When gas molecules are all moving in one direction, you get maximum amount of work possible. In other words, all heat could be converted into energy. And of course, the energy here, this is just a simple example of energy I'm giving you. On the other hand, the reality is these gas molecules are moving at random. So much of these energy is lost in randomness. Same thing happens when you go from heat to steam. Steam is nothing but water vapor. Then all these water molecules would not be useful in running the turbine or moving the turbine. In other words, you don't get much electricity out of that. That's why conversion rate is only 40%. So you try to avoid going through heat, and so try to get directly from chemical energy to electrical energy. Here we are showing you how we can calculate electrical energy. Delta G is the change in free energy, and which is given by minus NFE cell. Free energy is nothing but work other than mechanical work. Remember, it's the same free energy we discussed before. Free energy tells us whether a reaction is going to happen spontaneously or not. If it's a negative, it's going to happen spontaneously. In voltaic cell, it has to be delta G has to be negative, because you get spontaneously electricity when you join anode and cathode together. So this is how you can calculate delta G value, or work, electrical work. N, which number of moles of electron being transferred from one half cell to the other half cell. F, or Faraday, is a constant quantity. That means we know that 96,500 coulomb comes with a mole of electron. So keep that in mind. So if I know number of moles of electrons being transferred, multiply that by 96,500 coulomb, that means total coulomb that passes through would be known. And if you multiply that coulomb by cell voltage, which is given by oxidation contribution plus reduction contribution coming from two half reactions, and that would give you electrical energy. So if you look at these units, you see that moles of electron, that's the first quantity at the very bottom, moles of electron times coulomb per mole. So this is coulomb per mole times volt. So mole would cancel out. That gives you coulomb times volt, and that's joule. And that's electrical work. So basically, you need to know how many moles of electrons are being transferred from one half cell to the other half cell. Then, of course, you'll have to know cell voltage. Then 96,500 or Faraday is a constant quantity. Again, going back to the same type of reaction where zinc is giving off 2 moles of electrons, and copper 2 plus is receiving 2 moles of electrons, changing into copper. So let's apply delta G equals to minus NFE 0 cell expression to get electrical energy. Quite often students get confused about how do they get, they have a question in mind that how do we get number of moles being transferred. In order to know that, you'll have to work on half cell reactions and balance the half cell reactions. Make sure you have same number of electrons being transferred. So that means number of electrons given off in one reaction has to be the number of electrons absorbed by the other half cell reaction. If they're not same, you have to multiply in such a way that those 2 moles of electrons or number of electrons are the same. In this particular case, this is not a problem, so n equals to 2, because first reaction gives off 2 moles of electrons, and second reaction receives 2 moles of electrons, if you think in terms of molar quantity. So n is going to be 2 here, then F is going to be 96,500, and E0 cell is the cell voltage, which will be given by E0 oxidation for the first half reaction, and E0 reduction, sum of these 2 quantities. Now we're going to discuss effect of concentration on EMF or cell voltage. E0 cell, again, I wanted to remind you, stands for standard voltage. And E cell, when there is no superscript 0, that means non-standard voltage. That means you can have any pressure. Doesn't have to be 1 atmospheric pressure. To be in a standard state, if we are dealing with a solution, it has to be 1 molar solution. And if you're dealing with gaseous substances, it has to be under 1 atmospheric pressure, and temperature has to be 298 Kelvin. Say you have a sample of gas under 2 atmospheric pressure, or solution which say 3 molar concentration. That means you have to solve in this method, E cell, non-standard voltage. Here we are going to use what is called Nernst equation. Delta G is given by delta G0 plus RT log of Q. We already mentioned about this before. Remember the Q is defined pretty much like equilibrium constant, except those concentrations are not equilibrium concentrations. Remember, products raised to the power coefficient of balanced reaction divided by reactants raised to the power coefficient of balanced reaction. Now each of these delta G could be written down in terms of minus NFE. So you can see this algebra now, it's a simple algebra, minus NFE0 cell, and finally we end up with this. E cell or cell voltage would be under any situation, any concentration or any pressure would be given by a standard cell voltage under standard condition, and that value could be obtained from known values of oxidation and reduction potentials, minus RT over NF, and we already know what N is. N is number of moles of electrons being transferred. And again, as I mentioned before, in order to know that, you have to balance 2 half reactions. And log of Q, and we already know how to get the Q value. R value is 8.314 joule per Kelvin per mole is the ideal gas constant. Again, to remind you, E0 cell is given by E0 oxidation plus E0 reduction, and you get these values from appendix. In other words, these values are pretty well known for a lot of reactions. At 298 Kelvin, this is the final form of the expression. Basically, the top equation, the one that I'm showing you with arrow, when you plug in your number and when T is 298 Kelvin and do the math, you end up with this. E0 cell minus 0.0952 divided by N log of Q. This time is log base 10. In the above expression, it was log base E. So quite often, this is quite helpful. So we can use E0 cell minus 0.02952 divided by N log of log Q if you know the temperature is 298 Kelvin. Now, at equilibrium, we all know that Q value is equal to equilibrium constant, and delta G, change in free energy, is equal to 0. So if you use those values in this expression, delta G equals to delta G0 plus RT log of, I think it's getting a little messy here, RT log of Q. Now, when Q equals to equilibrium constant, so this becomes K equilibrium. I'm just showing you a little math here. Then this equals to 0, gets equals to 0. And then you can write down delta G 0 equals to minus RT log of K equilibrium. So this is pretty easy to remember. And K equilibrium is the equilibrium constant for the reaction that generates electricity. Now delta G0 is the standard free energy change. So that could be written down as minus NF E0 cell. And again, E0 cell, we can easily get it from oxidation and reduction potential values. And you can finally get this E0 cell in this form. You can write down in this form. At 298, you get a much simpler form and write down in terms of log rather than ln, which gives you N E0 cell divided by 0.0592. Here we're going to discuss problem number 60. So that's, let me write down 20.60. They gave a reaction where zinc solid reacts with copper 2 plus aqueous, giving zinc 2 plus copper solid. Now, question is, under standard condition, what is the maximum electrical work? So maximum electrical work that can be obtained if 50 gram of copper. So the question is, when 50.0 gram of copper is formed. Make sure you understand the question. So as you see that in this electrochemical reaction, copper is being formed. But the question is, if 50 gram of copper is formed in the reaction, how much electrical work would be done in the process of forming 50 gram of copper? So we're going to show you that calculation. Remember, we need to use this expression delta G0 because they're saying standard. Don't forget that under standard condition, they say that. So standard. So that means we're going to apply this expression delta G0 equals to minus NF E0 cell, because they're all under standard states, where N is the number of moles of electrons being transferred from one half cell to the other half cell. So we'll have to split that into two half reactions in order to know how many moles of electrons are being transferred. So let's do that, and this would be quite simple. Zinc and zinc, you have both sides zinc. So you have a zinc solid changes to zinc 2 plus aqueous, and I must have 2 moles of electrons to balance it. So that half cell balancing is done. The other half cell will be copper 2 plus aqueous plus 2 moles of electrons, giving copper solid. Now from the back of the book, Appendix E, page 1064, that's Brown and Lemay 12th edition book, you get these half cell values. The first one is oxidation reaction, but book gives you reduction value. Well, in order to get oxidation value, you just change the sign. The reduction value for this reaction was minus 0.763, so the oxidation has to be plus 0.763, because you reverse that reaction in order to change from reduction reaction to oxidation reaction. The second reaction, you keep it as it is, because the reduction value is known, which is plus 0.337 volt. Okay, remember that we need to know the cell voltage, which would be made up of E0 oxidation and E0 reduction. So the sum of these would give you E0 of cell, or standard cell voltage. And if you sum up these two numbers, you get 1.10 volts. Okay, let's now do this calculation. Here we know how many moles of electrons are being transferred. So look at the half reaction. The first half reaction has 2 moles of electrons given off. The second half reaction absorbs those 2 moles. If these two numbers were not the same, you have to multiply in such a way so that these two numbers of electrons are the same. So now N that is needed for this calculation is 2. That means 2 moles of electrons are being transferred when you have this above reaction that forms 1 mole of copper. So let's write down that delta G, that gives you the electrical work. So write down that delta G0 would be given by minus NF E cell. So I'm going to write down that again, minus NF E0 cell voltage. Now this is minus. The minus is because it's giving you energy spontaneously. So 2 moles of electron being transferred times 96,500 coulomb per mole of electron, and that's a constant. It's called Avogadro, it's all called Faraday. And then E0 cell, which we already calculated to be 1.10 volts. If you multiply all these quantities, you're going to get 2.12 times 10 to the power 5 joule. Now keep in mind, you get this much of electrical energy provided you have 1 mole of copper formed. But so let's write down here, that's relevant here, per mole of copper, because the question is about electrical work when 50 gram of copper is formed. So 50 gram of copper, we need to change it to mole of copper. So let's do that here. 50.0 gram of copper times, you know that how we go from gram to mole. Look at periodic table, and atomic weight of copper is 63.55. That's the gram of copper, giving a mole of copper. And this gives you a value of, let me write down the value, 0.787 mole of copper. Now, in order to get our answer, which says that when 50.0 gram of copper is formed, how much would be the work done, electrical work done? This is the quantity that I'm highlighting, is the amount of work done when there is 1 mole of copper formed. So now we have 0.787 mole of copper formed. So electrical energy would be given by 0.787 mole of copper times 2.12 times 10 to the power 5 joule per mole copper. And if you multiply these two numbers, you're going to get 1.67 times 10 to the power 5 joule. And this is my answer to this question. Here we're going to work on a problem in which from EMF or voltage, cell voltage, you'd calculate equilibrium constant. So this is problem number 55. So 20.55, and we're going to do A, part A. So let me write down the reaction, which is Fe solid plus nickel 2 plus aqueous, giving Fe2 plus aqueous plus nickel solid. Now, 2 slides back, I've given you equilibrium expression, equilibrium constant expression that relates EMF or cell voltage. And let me write down that in different ink. So log of K equilibrium is given by, just make sure that you have that right expression, N E0 cell divided by 0.0592. Make sure you know this equation is valid only at 298 Kelvin. And indeed, in this particular case, in these reactions, temperature is maintained at 298 Kelvin. In order to solve this, I need the N value. Remember the N value? What N means? Number of moles of electrons being transferred from one half cell to the other half cell. Secondly, I need the standard cell voltage. For that also I need, for both these information, I need to split this reaction into 2 half reactions. So let's do that. So first half would be reaction to be given by Fe solid becoming Fe2 plus 2 electron. That's 1 half reaction. The other half reaction will be given by nickel 2 plus 2 electron. Of course, keep in mind this is aqueous. Those pluses are all aqueous or water solution, giving nickel solid. Now E0 oxidation for the first reaction, we get it from back of the book, which is Appendix E. Appendix E has all the reduction values. So you need the oxidation value. So keep the magnitude same, change the sign, because if you change from reduction to oxidation, you basically reverse the reaction. So this becomes plus 0.446 0.40 volt. So the next one is the reduction reaction, half cell reaction, and that value we can just get copied as it is, minus 0.28 volt. So cell voltage would be given by E0 cell, which would be the sum of these oxidation and reduction values. That would be plus 0.16 volt. So now you can see that I got these cell voltage value. I also know N value. How? Because my half reaction tells me that 2 moles of electrons are being transferred from the first half cell to the second half cell. And those numbers will have to be the same. If they're not same, you have to multiply in such a way that those two number of moles of electrons are the same. Okay, now N value equals to 2. So we see that N equals to 2. And now we can plug in all these numbers to this equilibrium expression. So log of K equilibrium would be given by 2 times, remember N value, that's 2, E0 cell, which is 0.16, divided by 0.0592. We're looking at this expression. Let me point out to you. Divided by 0.0592. And this gives 5.405. 5.405. And this is log with respect to base 10. So you can use your calculator to get the inverse log or second function log. K equilibrium would be given by 2.54 times 10 to the power 5. Make sure you independently check my calculation. But this is how you're going to do equilibrium constant calculation based on cell voltage and not knowing the value of number of moles of electrons being transferred from one half cell to the other half cell.